Hey everyone, this is Matt with Learn Everything About Design, and in today's video we are going to be walking through the entire process of designing this engine cover that we did for my Kawasaki GPZ. So in our previous video, we just basically breezed through the process talking about what we're doing and why and how. And in this video, we're going to give you the opportunity to actually go through and design it on your own. So if you want to follow along, you can go to the description of the video, and the file will contain both the scan and it'll also contain the sort of hand traced scan of the cover. So you can use either one that you want to design. I am going to actually hide the mesh, and I'm going to focus just on the paper template and some basic measurements that I have. I think this is probably the most common way that people will be doing this if they don't have access to a scanner. So that's what we're going to be doing here. As I showed in the previous video, you can do this in pretty much any of the programs. So I showed that we can bring that piece of paper into plasticity, and we can do it in there. We can also bring it into SolidWorks, and we can work with it in SolidWorks. Bringing the mesh in SolidWorks is a little bit funky. You have to go into your add-ins, and then you have to enable scan to 3D, and that opens up some mesh tools. It's really kind of a pain unless you have something like Quick Surface for SolidWorks. But in this video, we're going to focus specifically on Fusion, because I'm going to be using Fusion for basically all the parts that I'll be designing for this bike, and I've got a long list of parts that we're going to be doing. So to get started, the first thing that we need is a basic understanding of the size. So I already have a scan in the file, and I already have, obviously, the paper. If you are just working off a piece of paper and a trace, then what you'll need to do is get a good idea of the rough dimensions and then some precise dimensions for things like the bolt holes, and as best that you can, measure the distances between the holes. I have all that information, and I actually did this initially probably about a year ago using just this paper method. I didn't use a 3D scan of any components. I just took the original cover, I traced it just like this, and I designed a cover, 3D printed, and put it on. So I have several of these, and I've done this a couple different ways, and that's why we're doing it this way. So to get started, we first want to begin by creating a new sketch on the front plane, and we're going to start with a circle. I know from basic measurements that the diameter of this is 127 millimeters. So you can see that it matches the sketch. If it didn't, we also have the option to calibrate our sketch. And that way we can pick 2 points on it, and we can say this distance between these 2 points is 127 millimeters. You can do the same thing inside SolidWorks. There is a calibration bar in there. Plasticity is a little bit different. The best way to do that in plasticity is to pre-draw your circle the right size and then scale the image accordingly. So now that we've got the 127, the next thing that I want to do is just add a secondary circle in here. That's going to represent this down here. The size, again, this is hard to measure. I estimated that it was about 70 millimeters, and then we can drag this around until we get it to the right location. I do think it's important for this type of design that everything is fully dimensioned, so I do suggest adding more dimensions, even if they're just kind of rough placeholders. So you can see here about 18 millimeters looks to be about the right distance, and about 30 millimeters vertically, and that puts it in a good spot. Now, again, this isn't perfect. If we were designing this for CNC machining, I would want to be more precise with these numbers. With 3D printing, the final part may be a little bit bigger or smaller depending on the printer you're using. I found, at least for me with the Bamboo Labs, the P1S that I'm using, it's actually pretty accurate. So if I was going to go ahead and CNC machine this part, which I've already got quotes for that, I would be fine going this route as long as the 3D print fit. All right, so we're going to finish the sketch, and then we're going to extrude. Now, I'm just going to start by extruding this inside section. These are going to be negative numbers, and basically because of the orientation of the parts, I could flip everything around so that the Y values were positive, but honestly, I don't care. For these one-off parts, it's not a real big deal for me for the coordinate system to be flipped like that. If it's a problem for you, then you can rotate the scan and the image and rotate them 180 degrees about Z. But in this case, I'm going to go up 10 millimeters. This is going to give me basically a good idea of how high I need to go to get close enough to where the casting is that holds the pickups inside this bike. So this specific bike runs what's called a wasted spark. Well, it's not typically called a wasted spark, but essentially what happens is the plugs fire both on the compression stroke for the power, and it also fires on the exhaust stroke. So there's only two pickups, even though it's a 4-cylinder. So they're on either side, and this is really the big thing that we need to make sure that we clear. So I'm going to hide the mesh again. I'm going to start by creating an offset plane. The offset plane is going to be going from here, so hold down the left mouse button, XZ, and we're going to come up a distance of minus 21 millimeters. Again, these were rough measurements that I got by holding up a couple of rulers and figuring out, basically if we've got one ruler that's an inch wide, that's 25.4 millimeters, I could see that I needed basically less than that to be able to clear. So playing around with these, I've printed a few, and I've done everywhere from about 19 millimeters up to 24 millimeters to kind of get a good feel for that size. With this, we're going to right click, create a new sketch. We're going to do a circle at the origin. And I figured that 100 millimeters was a good size, that we could create the taper, still having enough room to fit everything inside, and then we would gain a little bit of clearance while the bike is leaned over. So we can go to create, loft, and go from the top of our extrude to this, and join them together. The next thing I'm going to do is I'm going to hide the piece of paper. I'm going to go into my sketches, and now I want to extrude this piece up. So E on the keyboard, and we're going to come up a distance of minus 6 millimeters. In this case, this section right here, this little bump out, it's because the backside of this case, even though it's not holding oil, the backside of the case actually has a port drilled that goes into the oil passages. So it's part of the construction of the case in order to get the correct paths for the oil from the oil pump. So this section here, the only reason it's there is in case that plug fails and oil starts to come in, it gives it a low point. So it doesn't need to be very big. It just has to be strong enough to have enough structure there. So 6 millimeters is fine. Generally with something like this, I would avoid getting too close to this edge because it makes things like blending the corners with fillets just that much more difficult. So going up a distance of 6 millimeters, we're going to say okay, and then we're going to rotate this around. If you happen to be designing this with the mesh on, if we right click and make this unselectable, that will probably help your performance out because every time you hover over something that is selectable, Fusion has to highlight its faces. With a mesh, that's thousands of triangles, and generally it'll bog your system down. So now that we've got the basic shape, it's still solid, we're going to add some fillets. So I'm going to start by adding a fillet to this edge here, and I'm going to make it fairly large at 3 millimeters. Hit enter. And then we're going to do a fillet again, either F on the keyboard or right click to repeat. And I'm going to add a larger fillet, so 3.5 millimeters to blend that together. Hold down the control key, and then I'm going to select these other edges as well. So one of the reasons I'm using 3 millimeters and 3.5 really comes back to the fact that we're going to have to shell this thing out. We're going to have to make it hollow. If we make these corners too small, like if the radius value is smaller than the thickness value that we want to use, then we're going to end up with sharp corners on the inside. In this case, I actually want to try to shell it to 4 millimeters. And since we're 3D printing, it will leave a sharp corner on the inside in most cases, but that's fine. If you were going to be CNC machining this, however, you would want these outside radii values to be larger, or you would just have to add a fillet to the inside and just keep in mind that that radius is going to be the tool that's needed in order to create that cut. So here's our basic part. There's not a lot to it. This is really it, with the exception of the bolt holes. So as we look at this thing from the side, this is going to be quite a bit narrower than the original case, even though I'm still using the original pickups and everything on the inside. And the fact that it's tapered so aggressively means that as the bike is leaned over, it's just going to give me a little bit more ground clearance, kind of prevent things from catching. And since it's plastic instead of aluminum, if it does hit the ground, there is less of a chance of it catching. and grinding, the plastic will just kind of wear off a bit easier. So it's going to be more of a sacrificial part. If this is in a crash, it's not going to do anything to protect it. But honestly, the cast cover didn't do anything to protect it either. I have crashed the bike before, so I do know from, unfortunately, from firsthand experience that it didn't do anything. So now that we've got the basic shape, the next thing for us to do is to think about if we're going to shell this thing out and make it hollow, or if we're going to add the bolt holes to it. Now, it depends on the shape of the part that you're working with, but me personally, I prefer to shell this out first, and I'm going to go back and add geometry to the inside where the bolt holes need to be. So I'm going to go to shell, I'm going to select the back face, and I'm going to use 4 millimeters. This is going to give me enough surface area where it matches the case. So basically, it's about 4 millimeters wide where this touches the case. Any thinner than that, I could potentially have some problems, especially if I end up putting a gasket behind it. So that's where the 4 millimeters comes from. The next thing that I want to do is I want to add material back to the inside where those screw holes are. So if we bring back our cover scan, we can see the points where those bolt holes are. And now I need to add them. Another thing that I've done, obviously I've got the scan here as well, but another thing that I've done is I've measured the size of the bolt holes and the distance between them. So this helps me out because now I know exactly where they're located. So I'm going to start with a circle. I'm going to just roughly put it here. And I know that I want a 16.5 millimeter diameter. I'm going to repeat this process by adding another circle down here. However, I'm going to make these two equal, so I only have to control it with one dimension. Then I'm going to add horizontal vertical, because I know that these holes are going to be centered above the origin. And then I'm going to add a dimension that goes from the origin. And I know, again, from my measurements that this is 56 millimeters. And I know the distance to this bottom one is exactly the same. So I've got the distance between the holes. And now I know that 16.5 is going to be a little bit larger than what I need for the counterbore area, the flat area for the screws to sit flush. And this will give me enough material on the inside that I can play around with it. What we could do here as well, if you're worried about it, is we could go and just create straight lines. So for example, I could come from this horizontal section and come up. And then maybe we could project that inside edge. So if we go to project include, project, and we just bring that inside edge in, this will allow us to basically snap these together. So control, then we can add a tangency here. What this will allow us to do is create an extrude that doesn't roll back in. What I've found with this design is that little section there is so small, it doesn't really matter. Now, if I was going to CNC machine this, then I would likely bring this straight out or maybe even further out at an angle. That way I could have a larger radii value and I wouldn't have to have such a tight transition in there. And the main reason for that is because as you bring a tool in there, if you're doing, let's say, a contour into that area, and we've got, let's just say we've got a small tool. As we bring it in here, what ends up happening is it's contacting more than 90 degrees of the tool. And that's going to cause some chattering and some bad geometry in that corner. You can avoid that by doing a couple of other things like using different types of tool paths. But in general, I would try to avoid that if I was going to be machining this part. For our purposes, for a 3D print, I don't really care. So extrude, I'm going to take that section there and this section here. And notice that on this side, it's actually going all the way out. So this is problematic because I don't want that little piece on the outside. And you can see the sort of project include section here stops at that fillet. So what this tells me is I need to go back to that sketch and I need to project at least this here. So P on the keyboard to bring that in, and that'll give me just that inside section to work with. So now what we're going to do is, again, hit extrude. We're going to go to object, and we're going to join it together. So now we've got those pieces on the inside. This also gives us a sort of a concentric location for the rest of the geometry. So at this point, you need to think about, again, those fillets. When do we want to add and sort of round things off? Do we want to do it now, or does it make sense to do it later? I think that it makes sense to do it now, personally. And again, because we're not machining this, I don't have to worry about making this radius value fairly large. 2 millimeters is going to be fine. I don't have to worry about taking a 4 millimeter tool in there. If I was CNC machining it, again, I would make that quite a bit larger just so I didn't have to use such a small tool. I am going to hit the plus, and I'm going to add a couple more fillets in here. I'm going to see if I can round everything off. Let's make these 2 millimeters and see if it works. Rotate this around, and we'll do the same thing over here. So hold down Control, just grab all these edges, and looks like it's okay. And again, this section here, I think we could do a better job if it was being machined for a 3D print. Really not going to affect us too much. All right, so everything's going pretty good. Now we've got enough material on the inside of the cover that we can add the pads where those screws are going to sit and the holes that are going to go all the way through and allow for enough clearance. So in order to do that, I found that creating another offset plane is generally going to be the best way to do this. Now, I'm going to do this from the base, which is, again, this bottom plane here. And we're going to come up a distance that makes sense. Now, in my case, I measured this based on hardware that I have available, and 12.75 millimeters was roughly where I wanted to put the hardware. With shorter screws, that could be a lot lower. In a previous crash, the threads are a bit damaged on one of these holes, so having a longer screw go deeper down into the hole was kind of a key element here, at least for now. That way I don't have to drill out the hole and put a helicoil or something in it. So 12.75 works for me. Again, there's not really a requirement here, as long as the screw size that you're using can clear the stuff that's on the inside. And again, that's kind of where this boss that we added to the inside comes from, making sure that everything fits and that we can have enough room for that. So with this new construction plane, I'm going to start and create a sketch. I'm going to bring back sketch 4, and I want to take the center point of each of these holes, so holding down the shift or the control key, and then project them by hitting P on the keyboard. Then I'm going to hide that sketch, and I'm going to rotate this around because it's probably easier to see this way. So now we've got the center point locations for both of those holes. The screws that we're going to be using on this are going to be 7 1/4 diameter. That's large enough that the screw kind of fits in there fine. It's not a tight fit and it's not a super loose fit. There is going to be an offset for the counterbore though. So depending on the head of the screw that's being used, that's kind of where that's going to come into play. I'm going to go ahead and just put 2 holes or 2 circles on both of these. I'm going to make them equal. So the large ones will be equal to each other. The small ones will be equal to each other. This lets me just dimension one of them. So the inside hole, that's going to be the passing hole, 7.25 millimeters. The outside hole is going to have a 4 millimeter offset. That 4 millimeter offset, we can see here, is just inside of that boss that we added. And what this means is that could potentially be a very thin area. So once again, if this thing was being machined, I would probably look for a screw that had a smaller head size, something that I wouldn't really need to push the wall that small. And part of the reason for this is because we can't go too much bigger because of the stuff on the inside. Now, this is actually a cable. I could reroute that a little bit and be okay. But there's not a ton of room around the diameter of this thing. They actually had it fairly tight in that regard. But that's kind of something that we need to consider. So what I'm going to do is I'm going to draw 3 lines. I'm going to make sure that they're tangent. I'm going to make sure that both of these are vertical. And just for good measure, I'm going to add a dimension here of 10 millimeters. It just needs to be outside of the solid body that we have here. I'm going to repeat this process down here. So again, my line tool, I'm going to come down, over, and back. Make sure that they are tangent. And make sure that they are vertical. And I'm also going to make this line length equal to this one. So I don't have to add any other dimensions. You'll notice it's not fully defined. I'm going to hit escape, and we're going to see what can still move. So this seems to be able to still move. It should be equal, which should fully define it here. And since it's not, I'm going to go ahead and just add a dimension just to make sure. And I'll just click on this 10 millimeter dimension to make sure that they're the same. So now that we have all this information, we can finish the sketch and we can do an extrude. So I'm going to select everything I have here, hold down Control. We'll do the same thing over here, hold down Control. And this is just going to get pulled up. The distance will be through all. So now we've got that small little pad there, and that's going to give us an area where the screw can sit flat as we screw this thing down, and it's large enough for a fairly big, a large head on a screw, whether it's a socket head cap screw or something like that. We've got a lot of room to play with. Now we need to bring back that sketch again. Once again, extrude. This time, hold down Control. We're going to go down through all and say OK, and then hide the sketch. The last thing that we really need to do here is round things off. You'll notice that the flat spot here is not very big. That means the screw is going to kind of hang out in space. We're going to take care of that in just a second. Everything that we've done so far is parametric, meaning that we can go back and tweak the dimensions and have everything update. So we're going to address that in just a second, but I do want to add a small fillet here. So F on the keyboard, 1 millimeter just to round that off. Hold down Control and select this. There's really no need to do a fillet on the inside edge. If we were machining this, we would want to make sure that it stayed square, just so it's not super cumbersome anyways. And we can say OK. So now there's not a ton of room here. I would really like to have more space, so that way I didn't have the screw kind of sitting off in space here. And this is, again, the great thing with doing things with parameters is this plane right here, we can just simply change the height of that plane. So instead of minus 12.75, let's go ahead and do minus 10. And what that does is it's going to drop that plane down. You can see now it's cutting halfway through this fillet. Again, it's fine because we are 3D printing. And we can just simply make sure we still have enough material on the inside. It's always a good idea to go back and do a section analysis on your part. I'm going to flip it. And just make sure you have a very clear understanding of where material is and any thin sections that you might have to deal with. So we can see right here, that is a fairly thin section. That is going to be problematic. Again, if we were machining for our 3D print, probably not a big deal because, again, the intention of this part is to be sacrificial. If the bike gets leaned over and it starts dragging the ground, we want it to get worn away, and we don't want it to actually cause the suspension to unload, and then the front end becomes light and then a crash again. So that's why everything is kind of designed in this way. It's tapered. It's got, very minimal material in certain areas so that it is kind of sacrificial. But once again, everything here is going to be able to be changed by just tweaking dimensions. So we can come up here and we can say, maybe we didn't want this to be 4 millimeters. Maybe we wanted it to be 3. It may give us a warning about some additional feature like the fillet. Sometimes all you have to do is go back in, select the feature and rebuild it, or you can go to the option that we have to under modify to compute all, Control and B. Sometimes it's just as simple as that because it just needs to go back through and recalculate everything. In other cases, you might find that it does actually fail. In this case, it's going to be fine, but now we've got enough material around the hole. And as long as the screw size, the head size fits inside of that size that we dictated here, then everything will be fine. That's pretty much it in terms of designing it. You could certainly tweak things around the top because we used a consistent wall thickness. The top of this is actually fairly thick. It's 4 millimeters thick. It doesn't need to be. It could be thinner. Again, if we were machining it, that's something we would want to consider. Now that we've changed the dimensions a little bit, this wall has gotten a little thicker. That helps out, of course. And everything looks good. Okay. Another thing to consider is if this thing is getting 3D printed, we don't have to stick with such simple geometry. We could go as crazy as we wanted with this. But in reality, this part doesn't need to be super crazy. It's just a cover. It's really there just to keep dust out. Back in the 80s, when these bikes were raced by people like Wayne Rainey, they actually didn't even put the cover on the bike. They just had it open and exposed to air, and that's perfectly fine. It doesn't need to be covered. It could get wet. The main reason it's there, again, is just to kind of seal things off and keep dust and dirt out for a road bike. But that's pretty much it. If you want to, you can always go back and add more detail. I highly doubt that anybody out there is actually designing a case for a GPZ 750 like I am. But if you are, this part does fit on. You can 3D print it. You can play around with it, make some changes. I did a version of this with the logo on the outside, but honestly, it just complicates 3D printing, and I've just got a simple one here. Now, the last thing that we need to consider, since this is designed for 3D printing, is going to be the material. Certain materials are going to work better than others. A standard PLA may be fine, but probably not. The one that I'm using right now is a PLA CF, but there are other materials out there that have higher temperature and UV ratings that you may want to consider. I do strongly suggest doing test prints with PLA just to make sure that the part fits, because printing with like a PLA CF, the material is more expensive. If you're trying to do something like an ABS, it's obviously a bit trickier. It's harder to print with that material in most cases. A PETG or some of the other newer materials on the market can all be great options as long as you pay close attention to that temperature range. So there you have it. If you have any questions on this, please let me know. I am going to be doing quite a few more parts for this bike. This series has been planned for quite a while, and I just haven't gotten around to it. But we have rear sets and a triple clamp and several other brackets that need to go on the bike. But I also have body work that we're going to be doing, a tail section. I've got a headlight, some electronics, a GPS speedo, and a gauge surround for that. So all kinds of things have to happen for this bike. It's been a project for a long time, and I finally want to get around to finishing it. So if you have any questions on this, please let me know. If you want to see more of this, let me know, and I will keep filming as I design the parts. Otherwise, we can just do a basic build series where we don't go through every part. But if you all want to see it, then I am happy to record it. So that's it for this one. As always, thanks for watching, and we'll see you in the next one.